Welcome, everyone, to the seminar this afternoon, People and Sulfur, the Forgotten Elements Cycle. Seminar, of course, is in honor of the 2015 Volvo Environment Prize laureate, Professor Henning Rodhe. It's very appropriate, I think, that we have this seminar precisely at this time, because on the eve of the big climate conference in Paris, everyone is talking about the carbon cycle, of course. And we forget that there are many important element cycles in how the Earth system works. In fact, one of the very first pieces of evidence that the Earth operates as a system was actually part of the sulfur cycle, not the carbon cycle, with the discovery of the role of sulfur in DMS and in cloud and albedo. We'll hear a bit about that later. This afternoon's seminar will present many fascinating aspects of the sulfur cycle. And we're going to start with Professor Henning Rodhe himself, and he is a professor of chemical meteorology here at Stockholm University and has had a long career in atmospheric chemistry, particularly on sulfur compounds. So without further ado, Henning is going to give us an overview on human interactions with the sulfur cycle. Over to you, Henning.
Thank you very much, Will. When I spoke yesterday in Gothenburg, I had one of my brothers, the oceanographer, in the audience. And today, when I look out here, I have another brother in the audience, the hydrologist brother. There are still two more brothers, maybe to come some other time. I wanted to start with a few comments about, here we go, the sulfur cycle. And let's look at the cycle as we see it today. We have red circles represent human anthropogenic fluxes. One doesn't affect the atmosphere so much as the water, but the 60 units here comes out in the atmosphere from combustion processes, basically. And that is to compare with some natural fluxes, like biogenic gases, like dimethyl sulfide coming out of the ocean, some SO2 coming out of volcanoes, and some other biogenic gases coming out of soils. So if you add up, you can see today the 60 here is clearly bigger than even if you sum up all the green little things here, it doesn't come up to 60 in all. So we have passed the nature on a global scale here. In this graph, we have plotted the natural emissions, a wide range of uncertainty here, here in green, and then the anthropogenic emissions, how they have increased over the years. And you notice here that we reached a peak here somewhere around 1970, 80 or so here, and after that, emissions have gone down, especially in three regions here: Western Europe, North America, and Eastern Europe. The emissions have gone down by a large amount. If you continue here to 2000 to the present, the reduction in European sulfur emissions have been more like 80 to 90% compared to the peak in the 1980s. We'll hear more about the European situation by the next speaker, and on the Asian situation in the following speech after that. So this is what it looks like. And the question now, so on a global scale, we are surpassing the nature, but the sulfur compound, like all other aerosol-related species or reactive gases in the atmosphere, they are not spread uniformly in the atmosphere. So if you look in specific areas where the pollution emissions are especially large, then the man-made emissions dominate much more than what you can get from this figure. Take China, for example, or East Asia. Their anthropogenic emissions are much larger, maybe a factor of 10 or more. We will maybe hear about that later. So the question then, what's the problem? Why do we have to worry about sulfur in the atmosphere? And I'm going to focus on three specific problems: acidification, health, and climate. And let me start with acidification. And let me tell you this story. I mean, most of you heard about the story of how acidification hit Europe in the 1960s, and it was discovered and discussed publicly first by this person here, Svante Odén, who was a soil scientist from the Agricultural College in Uppsala. He wrote a paper in Dagens Nyheter, one of the big daily papers in Sweden, and in 1968. And that changed my life, I can say, from being a sort of traditional meteorologist before 1968 to becoming a chemical meteorologist from that particular date. The thing is that I read the paper by Svante, and where he described how things had become more and more acid here as you proceeded from, and he suggested that this is caused by sulfur pollution from UK mainly. And of course, that was a completely new idea. I mean, nobody thought that pollution could spread that far. Air pollution is supposed to be a local phenomenon affecting urban areas, etc., but not long range like that. So I was also part of that sort of idea. I read the paper and I called Svante up and said, I don't believe that what you're saying. It can't possibly be true. I mean, it's against all what we know about air pollution, dispersion in the atmosphere. And so he invited me to come to his office. So I went to his office in Uppsala, and I spent much of a day there with him discussing. And at the end of that day, then I became a chemical meteorologist. I was pursuing my PhD studies at the Department of Meteorology here in Stockholm. I had been working on a project given to me by Professor Bert Bolin on the circulation of the upper atmosphere, the winds in the upper atmosphere. But I decided to forget that and take this problem here, I mean, to verify or falsify Svante Odén's hypothesis. And it turned out that eventually that Svante was right, and we'll hear more about that by the next speaker, so I won't talk more about the European situation. But now I'm a chemical meteorologist, and I changed my direction a little bit more. At least I widened my perspective coming to the 1970s or early 1980s. I asked myself, so we know a little bit now about what's happening in Europe, and we know enough to motivate, to serve as the basis for mitigation of sulfur. And so that was a sort of a hopeful, positive development in Europe and North America. But what about the rest of the world? What about China? What about India, etc., where we knew that the sulfur emissions went up sharply? So I started to plot a map of the pH of rainwater in a global perspective of the world. But there was appallingly little data available outside Europe and North America, and some data in China, some data in Japan, but for the rest was virtually nothing. So from there, I decided to work with a model, and this is a simple, simple energy balance. Simple energy balance model based on these 4 ions in rainwater, in precipitation: sulfate, nitrate, calcium, and ammonium. So these sulfur, oxidized nitrogen, calcium, and ammonia, we know a little bit about how their sources are distributed over the world. So we can model how they are. We have chemical transport models, global chemical transport models, to simulate the distribution of these 4 compounds. And then, as a difference, as out of that, you can calculate the hydrogen ion concentration and basically the pH of rainwater. Now, with that model, then you can switch off the anthropogenic emissions and see what happened. What was it like, presumably before we started to pollute the atmosphere? This is what the result is. You have very high pH over much of the continental Africa and Asia because of the dust, soil dust. You have slightly acidic conditions over the ocean because of the DMS emissions, etc. So that's what you see. Now, in the Anthropocene, in the 1990s, where we are now, the picture is completely different. You have the acid blotches here over in North America, Europe, and some here, some little things here, some little things there. But it shows that we have completely changed the chemical climate of the world with our sulfur emissions. And next step is then to see, does it matter? I mean, yeah, we heard about the acidification in Europe. We knew about the acidification in North America. But what about here, Asia, especially? I was interested in, especially in Asia, East Asia, Southeast Asia, and Southern Asia, India. So I compared this deposition map then with estimates of the sensitivity of the soils in different parts of the world. And if you put this together, you see that there are 3 areas where you have both sensitive soils and high or low pH, high acidity deposition. Here, here, and here. Whereas in some other places where you have, I mean, up here you have still high sulfur deposition or low pH, and you don't seem to have very sensitive soils there. So that's not really much of a problem. India, where I've been working a lot, has very resilient soils, so you don't expect to see much problem there. Okay, so that was kind of reassuring, and we studied together with soil scientists and soils in different, especially in Asia, and going through the literature, we found that there is actually no obvious biological effects due to acidification of soils or surface water in Asia yet. I would say that we are close to the point where some Chinese soils might become acidified enough so that the base ion saturation will be depleted. But we are not there yet, as far as I know. There are some effects on vegetation, sure, of the pollution itself, but that's through the atmosphere, direct effects of SO2 hitting the vegetation. Okay, so that's it. Now we move on to health effects. And you heard this story probably before. I don't have to repeat the details here, but the very small particles that are formed in the atmosphere, I should have said that maybe, that sulfur, much of the sulfur pollution is emitted into the atmosphere in the form of a gas, SO2, sulfur dioxide. It's converted in the atmosphere by photochemical processes to sulfuric acid and to sulfates, various types of sulfates. Ammonium sulfate is a common chemical composition of aerosol particles in the atmosphere. So it's initially a gas, eventually a particle. These particles that are formed this way indirectly in the atmosphere, they are very small, often substantially smaller than 1 micrometer in size. So you can't see them, it's just very, very tiny. But they can penetrate into the lungs and cause problem, cardiovascular, and respiratory diseases like that. Recent estimates have it at 3 million people per year die globally because of indoor air pollution. Probably as much from, oh, I missed something here. Should be probably as much from, no, sorry, that's right, yeah. This is from outdoor, and this is indoor, probably as much, yeah. So we're talking about several million people dying, and the situation is especially severe in some Asian countries where you have very high concentration of this hazy air with not only sulfur, but sulfate, but other small aerosol particles. And people who cook and heat houses from small fires, indoor fires, women and children are particularly exposed to this problem. And so this is a really serious health issue that we have to consider. Even in Europe, and well, here when we talk about health effects, it's not just sulfur. Typical composition of aerosol particles in China, small aerosol particles, are sulfate, almost half, organic type particles, and some others. Black carbon, the soot part, is a very small fraction of the mass, but we will see in a little while that they are playing a very important role. So sulfate is not the only type of particle that we have to consider when it comes to health and climate, as we'll see in a little while. But even in Europe and US, North America, sulfate is still a large part of the particles. It becomes less and less sulfate in Europe because of the decreasing emissions. Even in Europe today, it's estimated that 400,000 people die prematurely because from air pollution. Much of that is small aerosol particles inhaled in the body. Sweden is supposed to be a clean country, but 5,000 people is still quite a number compared to our population here. So it's not a negligible people. It's not just an Asian problem. It's a general problem everywhere. The European particles are supposed to come not only so much maybe from open fire burning as in other countries, but from agriculture, ammonia emissions from agriculture, and from traffic in particular. Okay, now last part, climate. We have to understand that there are two types basically of particles when it comes to climate. We have the black particles, soot, for simplicity, and these particles can absorb radiation, absorb solar radiation, and they can thereby heat the atmosphere. And they cool the surface because this absorption prevents some of the sunlight to reach the ground. But on average, black particles warm the climate, our climate system. On the other hand, there are white particles. That's where we find our sulfates. Oops. Here, sulfates and the organic particles, they are white because they reflect solar radiation and they tend to cool the planet. So this is, we don't have to consider, mustn't consider just one type of particle. We have different types of particles and then behave very, very differently like this. Now, the question is that which one is biggest or most important? You compare the magnitude of these different aerosol effects. Then we use something called climate forcing, and that's an energy unit called watts per square meter. Energy watt per square meter. Soot warms the atmosphere on average by 0.6 watts per square meter over the whole globe, averaged over the globe. The white particles, sulfate, etc., cool the system by 1.4 in that direction. And you can find out for yourself that if you take the net, it's minus 0.8. So aerosol particles on average cool the climate. But I put in here also the uncertainty range. This number, 0.8, is extremely uncertain, going from almost nothing up here, 0, to minus 2 watts per square meter if you go down here. So we have to remember that that is mainly because some of the effects of the white particles are especially uncertain. Okay, so that's the net effect. How does that compare with the warming by greenhouse gases? Here we go. You have positive forcings by CO2. That's the main positive forcing, the main greenhouse gas, plus 1.7. You have methane, ozone, some other gases adding up to 1.3. And here we come again with the soot, 0.6. So you see, soot is not a negligible contributor to global warming. It's actually quite substantial, comparable, smaller but comparable in size. Okay, so we are talking about in the Kyoto Protocol and the Paris meeting is going to discuss mainly these gases that are covered by the Kyoto Protocol, CO2 and methane, etc. But this here, if we could get rid of that one, we could, I mean, imagine the corresponding cut in CO2 here by 0.6. It would be a huge improvement. But, all right, so there will be a focus, hopefully, on black carbon also. The problem is now that well, to take away black particles from the atmosphere is a win-win situation. It helps climate, it reduces warming, it takes away a health impact. The white particles are a little bit more complicated how one should look at them because they both mask warming, which is a positive effect in a sense, but they also have severe health effects, acidification, corrosion. I haven't talked about corrosion, but it's another side effect. So are white particles good or bad? Is sulfate good or bad? Sulfate particle good or bad? Well, you can phrase it a question like this. Should we place more emphasis on reducing black particles than on reducing white particles? Because it's more obvious that it's a win-win situation with the black particles than with the white particles. On the other hand, if you're focusing on health, you should really take away all particles, including both black and white. So, and also, even if you wanted to put more emphasis on taking away black particles, is it even possible to do that? That means that most of the emissions of particles are both black and white. The fires from the household cooking in Asia, for example, consist of both black and white particles and a mixture of those. So even if you wanted to focus on the black particles, there are a few sources where you can really, there are more black particles than white particles. That's, for example, diesel engines and some other industrial processes. But on average, in general, it's difficult to do that. Okay, so that's where we are with the particles. Now, final point here, but future climate. What determines the future climate? Well, we have emissions of greenhouse gases and of aerosol particles. And we have another thing which is not often always discussed, but so a key parameter is the sensitivity of the climate. Given that we have a certain amount of pollutants in the atmosphere, how much will the climate change? You look at this IPCC diagram where you show the projections of temperature into the future. And you have different scenarios here. The very optimistic scenario that we emit very little, we come down somewhere here. The more pessimistic or maybe realistic scenario, we're up here somewhere. The temperature by 2100 with several degrees warmer. Now the shaded range here represent uncertainty because of uncertainty in the climate sensitivity. If the climate is very sensitive, we will sit up on the upper part of the shaded area here or there. So first of all, it's emission, how much we emit that matters. But then it's the sensitivity of the climate system. We have tried to illustrate that in a paper called Why Hasn't Earth Warmed as Much as Expected, where Stephen Schwartz and some other colleagues and I were involved. That paper, because of this provocative title, we had some difficulties in having it accepted in the first place in a journal, scientific journal. But eventually, the bottom line is this: expected warming. If you take the IPCC estimate of the sensitivity of the climate system, we should have seen 1.8 degree warming by now. We haven't. We have only seen 0.8 degrees. How should we explain the difference? Well, here's where the cooling, the aerosol effect comes in. Either we have to subtract from here, we have to subtract the negative, the cooling by aerosol particles, or we have to say that IPCC estimate of the climate sensitivity maybe was on the high side. And we don't really know how this should be combined it's a big difference here. And the general feeling among climate modelers in the IPCC is that, well, it's mainly due to aerosol cooling here. But on the other hand, the uncertainty in the estimate of aerosol cooling is so large, so it could be, if aerosol cooling is very small, then there must be then we must have to reduce the sensitivity of climate, and vice versa. I hope you understand what I mean. Okay. I wanted to leave you with this concluding remarks then. There are very good reasons to reduce emissions of sulfur soot and all aerosol types and aerosol precursors, and mainly because of their effects on health. In the case of sulfur, also acidification, and then nitrogen oxide also. Climate, I put in the bracket just to indicate that it's a little bit more tricky to interpret sulfur white particle reduction in terms of climate. Next point is just what I just said a little while ago, that we need better estimate of current aerosol forcing, because that would make it easier for us to estimate the climate sensitivity better, which will make it better, more accurate prediction of future climate. Then the final comment before I end is that in the long run, if 50 or 100 years from now, it's the CO2 that is going to drive all changes in climate. CO2 accumulates in the atmosphere. It's a long lifetime. It accumulates in the atmosphere. Particles don't accumulate. As soon as we cut the emissions, they will disappear because they just stay for a few days or a few weeks. So aerosol particles may be important right now for various reasons, for health reasons and for this reason, but in the long run, it's the CO2 that we need to worry about. I think I'll stop here.
Thank you very much, Henning. Covered a lot of material in a short time, which is excellent. We do have time for a few questions before we go on to the next speaker. So I'm sure there are some issues that Henning's raised that would puzzle some of you out there. Yes, in the middle.
Henning, you showed maps where there seems to be sensitive soils in Asia, and they partly overlap with high sulfur deposition. And then you said that we have not observed any biological effects on acid rain in Asia. Isn't that very strange? Please repeat the question.
Yeah. Yes, I will repeat the question. Okay, he's referring to this figure here, and he's saying that there are overlap between acid deposition and acid sensitivity of the soils down in some parts, like here. Is that what you mean? Yeah. Why don't we circle that with a red ring also? Maybe I should have done that. I mean, it's at the present time, the acidity of rainwater is not very high when you come down to this part of the world down here. But in the future, we made some estimate of how long time will it take before acidification becomes a real serious issue. And we got down here in that area, we got up to 2 decades or so. For much of India, we said more than 100 years of acid deposition before we can expect serious problems. I would agree that there's a problem. Maybe we are unclear about how long time it will take here. It seems to be not yet very acidified, but sensitive soils. I don't know if I've answered your question, but so
Okay, we have time for one more question. Yes.
In the unmasking of the warming effect by sulfur aerosol, would that include as well as the sulfur aerosol load in the atmosphere decreases, it also decreases the cloud mitigation effect? So would that be taken into account?
The question is, when we talk about unmasking, if we are here, we're talking about sulfates, good or bad. And the question was whether this masking, if we unmask now, we reduce sulfur emissions, and therefore the sulfate particle concentration in the air, we unmask this cooling effect. And the question is, does that take into account also our calculation here, the change in cloudiness or the change in cloud albedo? Yes, I would say yes. It's the cloudiness effect. If you look at this bar here, this here represents both the direct effect in cloud-free air and the indirect effect on cloudiness of the particles. So it's taken in here.